Hi everyone, Mr. Fig back again with another lesson. This lesson is going to focus on convex mirrors. Last week we looked at ray diagrams for concave mirrors, and we developed those three rules for drawing ray diagrams for a spherical mirror. We're going to apply those same rules this week to a convex mirror. But first, I'd like to take a little bit of time to review what we saw with the concave mirrors. If you recall last week, we started by looking at an example of the kind of reflections you see if you simply look at a shiny spoon out of your kitchen drawer. This first spoon here, where you see the image reflected inverted, that is an example of a concave mirror. The bowl of the spoon curves away from you. And last week we developed the rules that why that image is that way. Now, when the spoon curves towards you, that is a example of a convex mirror. So the words concave and convex simply describe the shape of the mirror. Again, when the bowl of the spoon is curving away from you, that's concave. When the bowl of the spoon is curving towards you, that's convex. And again, and last week, we created ray diagrams that predicted that when we would see this inverted image in the spoon. So let's recall what those rules of ray diagrams were. All right, there are only three rules. Now, these rules weren't magic. They just came from the basic law of reflection. That is, the angle of the light ray striking the mirror must be equal to the angle of the reflection when measured from a normal line, which is a perpendicular where that ray hit. But we didn't need to worry about normal lines because we know how circular geometry works. So the first rule was any incident ray parallel to the principal axis, that's the center line of the mirror, would reflect through the focal point. And remember, the focal point is the distance halfway between the center and the mirror. Rule number two was when an incident ray that passes through the focal point and then strikes the mirror, either through or from a focal point and strikes the mirror, would then reflect parallel to the principal axis. And finally, rule number three is any incident ray passing through or from the center of the mirror would reflect right back along itself back through the center. And again, these three rules are so important, so you have them written down somewhere to keep as a reference, because again, these are the only three rules we need to do a ray diagram for mirrors. We're going to see three very similar rules, if not exact, when we talk about lenses in a couple of weeks. So for concave mirrors, this led to three possible solutions to an image. Oh, but before I talk about that, let's remind ourselves what the variables that we need to keep track of for these mirrors. It's a little confusing at first because there's a lot of details. On these mirror diagrams, what we label C is the center of curvature. That's basically the equivalent of the radius of the sphere. That, if I imagine the mirror was a complete sphere, what the radius of that sphere would be. What we call F, the focal length, it works out to be the distance that's halfway between the center of the mirror and the edge of the mirror. The distance between the object and the mirror, as measured along the principal axis, we call the variable P. Now, some books actually refer to this as DO for distance to object. So if you're on the web and you're looking at other video sources, they might refer to this as DO. We're using the traditional variables because that's what's in our textbook where we use P. Now, the distance from the mirror to the image that forms, that we use the letter Q. And again, we use Q because Q looks like the reverse of P, so it looks like a reflection. I remember it that in the alphabet, the letter P becomes before Q, and in reflection, you have to have an object before you have an image. And again, some books would refer to Q as DI, that is distance to the image. So you might see that out there on the web. HO stands for how tall or the height of the object, where HI stands for the height of the image. Okay. Now, when we applied those rules to a concave mirror last week, we saw that there were three possible solutions. All right, so let's take them one at a time just to review, because it turns out that a concave mirror is really not that complicated. A convex mirror is simpler than a concave mirror. For the concave mirror, if P was greater than F, that means that the object is further from the mirror than the focal point. So here in this picture, I have an object. Here's my focal point. I am further away from the mirror than the focal point. That resulted in these two light rays crossing right here, where an image is forming in front of the mirror. That image is inverted, it's upside down, and it's real. And again, a real image is one that I could shine on a piece of paper. So if I had this real setup in the lab, I could put a piece of paper where this image is forming, and I could shine that image onto the piece of paper. Notice that when the reflections bend inwards towards each other, we call that converging. So these are converging reflections, and a converging reflection will always make a real image. You can also spot a real image because from a single mirror and later from a single lens, a real image will always be inverted. So when you go to the movies to watch a film, if the image on the film is actually upside down from what you're seeing because they're shining it onto a screen. So the next case we looked at is what happens if the object is closer to the mirror. If the object is closer to the mirror, that's saying that P, or the distance to the object, is less than the focal point. So here's the focal length, or the focal point, the distance between the focal point and the mirror. And I see that I've placed my object closer. Now in this case, when we applied those same three rules, a parallel ray reflecting through the focal point, a ray coming from the focus reflects parallel, we saw that they did not cross on the real side of the mirror. And as we did with plane mirrors, if the reflections do not cross on the real side, we project those reflections backwards to see where they do cross. Here, the two reflections cross behind the mirror, and I get a large virtual image. This image is upright, it's virtual, and it's virtual because there's no way for me to put a piece of paper behind the mirror and shine that image onto it. I can see the image with my eyes because it seems like the light is coming from that point, but I can't stick up any sort of projection screen behind the mirror and see this image. And again, note that here, unlike in the first picture, the reflections are spreading out from one another. They're not crossing on the real side. We call this diverging reflections. And again, we'll see this with lenses as well. If my reflections diverge, if they spread out, that's going to result in a virtual image. And also, if I have an image from a single mirror or a single lens, if that image is upright, it's going to be a virtual image. There was a third case with the concave mirror, and that was if I stuck the object exactly on the focal point. When I stick the object exactly on the focal point and try to apply my three rules, what I find is here's again is an incident ray parallel to the principal axis. It reflects through the focal point. I'm sending light ray from the center, strikes the mirror, bounces back through the center, and I see that these light rays are parallel. When they're parallel, the light rays are not going to cross on either the real or the virtual side. And so in this case, I'm not going to get either type of image. There will be no image. So when an object is exactly on the focal point of a concave mirror, all you're going to see in the mirror is a blur. You're not going to be able to see the object. Okay? And that just summarized what we did last week. So what is it about convex mirrors? Well, let's take a look. So we're going to apply the same three rules to our convex mirror. Here is an example of a convex mirror. I have an object in front of it, and I see that the mirror is curving away, like the examples with the spoons. Now note in this when I have this type of mirror, that the focal length and the center of curvature are on the virtual side of the mirror. They're not on the real side where the object is. So it's a little bit tricky at first to apply our rules. But if we're careful and do what makes sense, it's not that hard. So let's start with sending a ray to the mirror that we normally do. I will send a ray parallel to the principal axis. Well, here's light from the top of the candle striking the mirror. Now, I know wherever this light ray strikes, there should be a normal line perpendicular to the mirror, and I know the reflection should have the same angle on the other side of that normal line. So as I move my mouse, you can probably guess that the reflection should be going somewhat upwards in that direction away from the mirror. So how do I figure out exactly where? Well, what I'm going to do is I'm going to draw, I know that a incident ray parallel to the principal axis should reflect as if it was coming from this focal point. So I would use a ruler to set up a reference line from the focal point to where this light hit the mirror. And it's important to remember that a light has to stop when it hits the mirror. A light ray isn't going to go through a mirror, it's going to reflect. So I don't bring this through the mirror, I stop at the mirror. Since it's parallel, I line up on the focal point, and I send my reflection as if it was coming from this focal point. So there's my first reflection. Well, I need to draw another incident ray from the top of this candle in order to figure out where the image is going to be. I've already done the ray parallel to the principal axis. I'm going to choose to send a light ray towards the focal point in this direction. Again, it's important to remember that when I send the light from the candle to the mirror, I have to stop at the mirror. The light ray can't go through the mirror. So let's send our reflection to the mirror. Now, this light ray is going towards the mirror. This incident ray is going towards the mirror in the direction of the focal point. Well, I know how that reflects. That should reflect parallel to the principal axis. And there are my two reflections. Note, I have two reflections. They do not cross on the real side. They are diverging, so I expect a virtual image. I'm going to do the same trick we did with plane mirrors. Since the reflections do not cross on the real side, I will project them backwards to see where they cross on the virtual side. They cross right there. So my image, the top of the candle image, should be right there. And again, I point out that since the bottom of the object is on the principal axis, the bottom of the image will also be on the principal axis. And I will get an image right here. This image is virtual, upright, and reduced. Now, again, it's virtual because there's no way for me to stick a piece of paper behind the mirror and project that image of a candle. And again, following the same rule, if I have an upright image from a single mirror, you know it's virtual. You will not be able to project it. Now, this diagram might seem a little bit more complicated than a concave mirror, but the good news is, unlike a concave mirror, a convex mirror can only do one thing. It will only make a virtual image, and that virtual image will always be smaller than the original object. Always. It's a one-trick pony. So once you know how this diagram works, there's no other way for the diagram to look. So that's all a convex mirror does. Unlike the concave mirror, reflections from a convex mirror will always diverge, so they will always make a virtual image. And it will always be smaller than the original object. Now, the next lecture video will be on the mirror equations, because so far we've used geometry to figure out these ray diagrams to see what type of image we get. But it's a little cumbersome. I have to be really careful with my angles. If I want to get actual numbers out of these pictures, I would need a ruler and measure the scale. So at this point, though, it would be probably a good time to stop and watch the video I've posted where I actually do some demonstrations with a concave and a convex mirror, and then pick up with the mirror equations after that. Okay, see you in the next video.